Hello, anyone who's watching this. This is paper 2, 2017. So it's the organic paper. I've done the multi-choice already to this, so this is just the written answers. Do me little thing here. Surname. Surname Norton. There we go. First name. Doctor. Funny that, isn't it? Right, next. So first page, I'm already seeing this Maxwell-Boltzmann distribution curve. You should be totally fine with these. If you're not, go back and learn it. Maxwell-Boltzmann distribution of molecular energies of a sample of a gas. Yes. Label the horizontal axis. Energy, sometimes known as energy E, but not just E. You can't just call it E. You don't need to put any units on. It's just a unitless graph generally. On figure 1, sketch a distribution of molecular energies at higher temperature. If you increase the temperature, more particles get more energy. So the peak is going to be over in this direction. The peak will shift this direction. But you're still tethered to 0. So it starts at 0 and goes down and ends up higher. Like that. So the peak goes down and to the right. My board is very wobbly today, which is going to really annoy me. Why are you wobbling? Hang on a sec. Just going to shim it up a little bit. A little bit. Okay, so that's what they're after. To the right for 1 mark, I imagine. And lower. And you also need that origin at that point. Okay, practice them. Very straightforward. The gas decomposes on heating. So there's a gas and it decomposes. Explain why an increase in temperature increases the rate at which this gas decomposes. So just the rates of reaction. So when you increase the temperature, so you can imagine that there's a theoretical activation energy here, EA. At the lower temperature, that many particles have got the energy required to react. At the higher temperature, more particles have got energy greater than or equal to EA. So at higher T, more particles have energy greater than or equal to EA. And if it was the exam, I'd make sure they knew what EA was, which is the activation energy. So that means you get more frequent successful collisions. I think that'll be it. I'm just going to check the mark scheme that's it. So more particles with energy greater than EA, so more frequent successful collisions. Yep. Next. I always worry when I see a calculation, but they're alright, aren't they? An experiment was carried out to determine the relative molecular mass, MR, of a volatile hydrocarbon. Right, this wobbly desk is actually doing my head in. This is very professional, isn't it? So, let's see if I can get it shimmed up. I'm not even going to edit this out. You're just going to have to live with it. A little bit of an insight into my life. There you go. Yay. Fixed. We're looking for the relative molecular mass of a volatile hydrocarbon X. That is a liquid at room temperature. They're just trying to scare you with words. Volatile hydrocarbon is a hydrocarbon that boils easily and turns into a gas easily, but it's a liquid at room temperature. The known mass of X, we've got a mass. It was vaporized at a known temperature and pressure, and the volume of gas was produced measured in a gas syringe. So it sounds like they've got a bit of a, probably wouldn't have used this sort of setup, but a liquid here. They've heated the liquid, it's turned into a gas, and they have collected the gas in a gas syringe. So this liquid all turned into gas and the gas is collected there, so they can see the volume of gas produced. All right, 0.194 milligrams. Sorry, not 194 milligrams, that's 0.194 grams. You've got to be good at that conversion. Kelvin I like, kilopascals. This is going to be a PV equals nRT question, basically. 102,000 for kilopascals need to be in pascals. Centimeters cubed needs to be in meters cubed. And this one often catches people out, but the easy way to turn centimeters cubed into meters cubed is to times by 10 to the 6, and now it's in meters cubed. the more you practice these, the easier they are. They're just dead straightforward. So PV equals nRT questions are always just about the units. Calculate the relative molecular mass of X. So what I need to know is how many moles of X there were. Well, anyway, let's just have a look at what I've got. PV equals nRT. I've been given a pressure, I've been given a volume, I've been given R, which is there, I've been given T. So that means I can work out N. You need to be able to rearrange this equation then. If PV equals nRT, if I divide both sides by RT, PV divided by RT equals N. That'll give me the number of moles. So then you're just going to be plugging the numbers in. 102,000, that's P, times V, which is 72 times 10 to the... You know what? I made a mistake. Minus 6. Sorry. Minus 6, of course it is. Good job I realised that. Times 10 to the minus 6. It was, yeah, 10 to the minus 6 meters cubed. Well, I noticed it, so whatever. 8.31 times 373. Plug all those numbers in, and that'll give you the number of moles. Now I'm going to cheat here by looking at the mark scheme briefly. So, okay, so I'm right. Good. Good job I spotted that mistake. 0.0024 moles. That will get you 3 marks. 1, 2, 3. One for the rearrangement, one for getting all the right numbers in, and then one for the calculation. Then I've got moles and I've got a mass, haven't I? I've got a mass up here. Oops, got a mass. So I've got moles and a mass. Mass, Mr. Moles. Some of you still struggle with this. I mean, I still have to remind myself of it, but I've got a moles and I've got a mass, and they want me to work out MR. So MR equals the mass divided by the moles equals 0.194 divided by 0.0024. That gives you an answer which you get a tick for, and then the final one is appropriate number of significant figures. If I have a look through here, the least precise value here is 72, which is 2 sig figs. Cool. So you needed the 2 sig figs. Next, analysis of a different hydrocarbon. Oh, these are so straightforward. Goodness me. Analysis of a different hydrocarbon. Empirical formula questions. If you're one of those people who just, I never quite got them. Oh my word, you're missing a trick. They're so easy. Hydrocarbon. Hydrocarbons are made of hydrogen and carbon only. Whenever you see empirical formula, I want you to write the elements at the top. We are 83.7% by mass of this, so the rest must be hydrogen. A little bit of quick maths, that's 16.3. I hope I've done my quick maths right. 16.3. Yeah, 16.3. What you then do is you drop this down, you divide that by 12, you divide that by 1. 83.7 divided by 12, that's going to be about... that's going to be about 7, isn't it? I'm going to have a look at the mark scheme. 6.975, cool. 6.975, 16.3 is, divided by 1 is 16.3. So that's a ratio. It's not a particularly useful ratio. We need to turn it into the simplest ratio by dividing both by the smallest number. I'm going to do that on my calculator on the computer. So what am I doing? 16.3. So I'm going to divide both sides by 6.975. Divided by 6.975. Now what you hope for here is a lovely little ratio pop out. It doesn't look like it will here. So I'm just going to type in 16.3 divided by 6.975, 6.975. And I've got 2.33. But 2.33 is basically 2 and a third. So if I times both sides by 3, I'll get whole numbers. So that's 3 to 7. There's your ratio. Alright. I couldn't round that to 2. This is not a 1 to 2 ratio. This is a 1 to 2 and a third ratio. So I need to times both sides by 3 to get whole numbers. Empirical formula C3H7. That's the simplest ratio. the molecular formula. So they tell me that the MR equals 86. So firstly, I'm going to check whether C3H7 equals 86. 12 plus 12 plus 12 is 36. That equals 43. I'm told that the MR of the actual molecule is 86, which is 2 times 43. So the actual molecular formula must be C6H14. Mark scheme, boom, smashed it, 4 marks. Alright, compounds A, B and C all have the molecular formula C5H10. C5H10, okay, so not an alkane, is it? Alright, C5H12 would be an alkane. A and B decolorise bromine water. That is a clue for saying they contain double bonds, but C does not. I'm going to write these little thoughts down now. Already I'm thinking A and B have got an alkene or an alkene. C, which has got the same formula as an alkene, I'm thinking cycloalkane. So I'm thinking this as I'm reading it. B exists as 2 stereoisomers, which again suggests that B has got EZ isomerism, because we've done that stereoisomerism already. And A does not show stereoisomerism. So A is an alkene, but it doesn't show stereoisomers. Use this information to deduce a possible structure for each of the compounds A, B and C and explain your deductions. Alright then, so C is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Because it doesn't decolorize bromine water, no double bonds. So no reaction with Br2. Is that enough of a deduction, do I think? No double bonds. You could say, probably better way than saying no double bonds, you could say it's saturated. Right. A and B must contain C double bond C, or they'd be unsaturated, or another way of saying that is they are unsaturated because they react with bromine water. So here are some suggestions then. I'm just going to go through a few examples. I'm going to put 5 carbons in a row. I don't know the answer yet, so... Right, so you can have a double bond there or a double bond there, can't you? That's it. You can have a double bond there or a double bond there. You could have other ones, like 4 in a row and a C there and stuff like that, but I'm just keeping it simple. Alright. 1, 2, dun, 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 dun. Dun, 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 dun. Right. What are we told up here? A does not show stereoisomerism. Okay. This must be A. Just going to rub this one out for a sec. This doesn't show stereoisomerism because one of the carbons of the double bond has got 2 hydrogens attached, 2 identical groups. So it doesn't matter if these hydrogens flip over, it's going to be the same molecule. It doesn't matter if you flip all these groups over, this carbon over, sorry, it'll be the same molecule. So this that must be A. B must be 1, 2, 3, 1, 1, because this can show EZ isomerism. What I've drawn here is I've drawn the hydrogens on the top and the large groups on the bottom on the same side, so that's the Z isomer. Then you could rotate this. I'm going to draw the E isomer. One, 2, 3, 4, 5. Sorry, should have dropped off the screen again. So we're just going to grab another coloured pen briefly. The Z isomer, I've put the small groups on Z same side, and then I've put the small groups on Z opposite sides. I could have drawn it in that other way that we draw EZs with H and H sort of a bit bent like that, but this way is fine. So that's the Z isomer. This is the E isomer. Right, so what else have I got to do? State the meaning of the term stereoisomers. Stereoisomers, you'll have to do that for a mark. Stereoisomers have got the same structural formula, but a different arrangement of atoms in space. How do they arise in compound B? Because there's no free rotation around this carbon-carbon double bond, I'd write that. There's no free rotation around the carbon-carbon double bond. So these two molecules are different. Right, I think I'm done. It comes though, that all came from looking at the formula. I knew, so straight away, let me just talk through the main things. I looked at that and I thought, alkene. I then thought everything about alkenes. Bromine water is a test for alkenes. I also know straight away that alkenes and cycloalkanes are functional group isomers of each other. So remember isomerism, functional group isomers of each other, and then EZ is over here. If this diagram doesn't mean anything to you, look it up in your notes. Right, when alkanes are burned in an excess of oxygen, they produce carbon dioxide and water. That is true. Write an equation for the complete combustion. Write an equation, start off with an arrow. Propane in oxygen. Right, oxygen is there, propane is C3. I bet loads of you wrote C5, didn't you? Because it's a weird, common mistake. C3H8, propane, double it and add 2. Carbon dioxide and water. C3, you'll make 3 carbon dioxides because there's 3 carbons. H8, you'll make 4 waters, 4 H2Os. Now it's oxygen 6, 7, 8, 9, 10, 5 O2. Right, next. An expression can be derived using bond enthalpy data to estimate the enthalpy of combustion of an alkane. For an alkane with N carbon atoms, delta HC equals minus 496 lots of N times, so 496 times the number of carbons, and then you add 202. The enthalpy of combustion of an alkane was calculated to be minus 6550. Deduce the molecular formula of this alkane. Okay, so delta CH, remember I would normally write delta HC, anyway, equals minus 496 N plus 202. And I'm told that this number is minus 6650 equals minus 496 N plus 202. So then, what can I do there? I can rearrange this, can't I? So that's a minus number, so 6550 equals 6650 equals 496 plus 202. 6550. So because there's a minus on both sides, that was. Sorry, I'm thinking out loud. I'm trying to work it out myself. I want to get the ends on their own. So 6650 minus 202. So I'm taking that 202 and putting it over there. Equals 496. And do this. Divide both sides by 496. I remember the answer to this one. I think it's 13. Let's have a look on the mark scheme. 13. Right, anyway, so that's how you do that. Oh, that is not the answer though. That's so N equals 13. N is the number of carbon atoms, so it's an alkane C13H, double it and add 2, 28. Suggest one reason other than use of mean bond enthalpies why a value for the enthalpy of combustion of a liquid alkane is different from the value obtained using the expression in question 4.2. Why a value for the enthalpy of combustion of a liquid alkane is different? Right, this is going to be to do with this, a liquid alkane. Suggest one reason. Well, if the expression is for a gaseous alkane and then you're using a liquid alkane, That could be one reason. Also, in delta H combustion expressions, if I was to write a delta H combustion here, so this is all about delta H combustion. Delta H combustion makes liquid water, whereas actually in real life you make gaseous water. So the delta H combustion, everything's in the standard state, in their standard state, and you make liquid water. But in real life, when you burn something, you don't make liquid water, do you? You make steam. So that was to do with state symbols. Not that happy with how I answered that, but anyway. Value of the enthalpy change for the combustion of 1 gram of some alkanes are shown below. So they've taken a gram of alkane, they've burnt it, and they've worked out how much energy is given out. Right, so methane, ethane, propane, butane, pentane. Do I have to plot this graph, or can you plot graphs? Actually, I've seen enough of your graphs to know that you're terrible at plotting graphs. Right, number of carbon atoms, 1 carbon atom, so that's going to be methane, minus 55.6. Minus 55.6. Ethane, minus 52. Minus 52. Propane, I haven't got a value. Butane, minus 49.6. Butane is 4, minus 49.6. I'm being precise. Minus 48.7 for pentane. 48.7. That, right, is looking for all the world like a curve. If it looks like a curve, it is a curve. Something like that, innit? Something like that. I don't know what accent that was. Okay. Smooth best fit curve. Value from the best fit line. For 3 carbon atoms. So what it's saying here is draw a best fit line, which I've done. So that can be a curve. Use this to estimate the enthalpy change for combustion. So we're looking around about here. That's my estimation. Minus 50.567. Minus 50.7. Cool. I'll do. Anything else I need to do? And use this to estimate the enthalpy change for combustion. No, that's it. I'm just a bit confused here because that looks like a really easy question. Okay. Isooctane. 2,2,4-trimethylpentane. Thing is, right, no one will watch this video. I'm talking to myself. I get like 2 emails saying thanks for the video, and then no one else watches them. So I can talk to myself. No one will ever know. Isooctane 2,2,4-trimethylpentane. Don't know if I need to draw it, but I'm going to draw it anyway. There's pentane. 2,2,4-trimethylpentane is an important component of petrol used in cars. When isooctane is burned, the enthalpy changes minus 48 minus exothermic 47.8 kilojoules per gram, not per mole, per gram. So there's probably going to be some moles shenanigans here. Isooctane is a liquid at room temperature with a density of 0.692 grams per centimetre cubed. And what that means then is if you have a centimetre cubed, and this is about to scale, a centimetre cubed of isooctane, it will weigh 0.692 grams. A little cube of it like that would weigh that many grams. Remember that water weighs 1 gram per 1 centimetre cubed. Okay. Calculate the heat energy released if 1 decimeter cubed of isooctane burns in excess oxygen. Alright, well I'm told the kilojoules released per gram burned, and they want to know what happens if I burn a litre. So if I can find out what that weighs, that should be alright, shouldn't it? Alright, I've got 1 decimeter cubed, which is 1,000 centimeters cubed, which is 1,000 of them. And I know that one of them weighs 0.692, so 1,000 of them will weigh 692 grams. That's easy enough. Alright? People get freaked out by density. It just tells you how many grams a centimetre cubed weigh. And then I told you I've got 1,000 centimetres cubed. It's a unit conversion question, basically. So I've got 692 grams of isooctane. And look at this number. Minus 47.8 kilojoules of energy are released when you burn a gram. and I've got 692 grams. All right, so I'm going to have 692 lots of this value. 692 times 47.8. 692 times 47.8. Calculator. 692 times 47.8. 33077.6. 33077.6 kilojoules. It really helps, doesn't it, to just look at the look at the units and say them out loud. Kilojoules per gram. Alright? And I've got this many grams. I don't know I had this many grams because 1 litre and each centimetre cubed weighs this many grams. Give your answer to the appropriate number of sig figs. What's the appropriate number of sig figs? 1, 2, 3 sig figs. 3. And they want it in kilojoules. 331. 33100 kilojoules. If you don't do that, you've lost the mark, even if you're really clever. Okay, next. What am I on? 26 minutes. I'm going fairly quick. Ethane dioic acid is a diprotic acid. Diprotic acid. I'm going to draw it out for you. Come across it a bit more. Ethane dioic. It's an ethane. What do you call it? Carboxylic acid on both ends. Ethane dioic acid is a diprotic acid, which means that it's got a proton here that can be lost and a proton here that can be lost, an H plus there and an H plus. So when it loses that, it tells you down here anyway. So when it acts as an acid, it forms this, and 2 H pluses are released. Anyway, a student carried out a titration with sodium hydroxide to determine the mass of the acid in the solution. So beekeepers use a solution of this other pesticide. A student wanted to know basically the mass of the acid in the solution. The student repeated the titration until concordant titers are obtained. Titration calculations are always easy, but they will try to make them sound difficult. Right, the student found that 20 centimeters cubed of the ethane dioic acid solution. So I do VC, volume and concentration, and I collect information. 25 centimeters cubed, so that's 25 centimeters cubed. I've used this of the ethane dioic acid, reacted completely with 25.3 of a 0.5 molar sodium hydroxide solution. Calculate the mass in milligrams of the acid. You've got a C and a V. If you've got a C and a V, you can do C times V over 1,000 and you'll work out moles. So I'm going to do that now. C times V over 1,000, that's 25.3. 25.3 times 0.5 equals, divided by 1,000 equals 0.0125 moles. 0.01265 moles of sodium hydroxide. The sodium hydroxide probably came out the burette by the looks of things. Moles of this. What I then do is I use a ratio arrow because 2 sodium hydroxides react with 1 ethane dioate. So I'm just going to, ethane dioic acid, sorry. So I'm going to divide that by 2 on the calculator. Divided by 2 equals 0.006325 moles. I'm going to write the word moles of H2C2O4. What do they want to know? Mass. I've got this many moles of it, got this many moles, and I've got a formula. Yeah, so I can work out an MR. Moles times MR equals mass. What's the MR of that? I'm going to go to the mark scheme now because I can't bother working it out because I'm on the easy bits. MR equals 90, so it's this number times 90, and that'll give you your answer. Sig figs. It's going to be 3 sig figs in it. 569, apparently. Milligrams. Where are you getting that from? This will give me an answer in grams. 0.006325 times 90 will give me an answer in grams. And then to get it into milligrams, I'm going to have to times it by 1,000 because there's 1,000 milligrams in a gram. So there's always a place in it. So basically there's 3 marks here for being good at chemistry, and there's always a 4th mark for being good enough at chemistry that you are relaxed enough to notice that they want like a unit conversion. So just being good at chemistry will get you 3, like really good at chemistry, well done you. And if you keep consistently getting that 4th mark as well for doing the unit conversions, you're just on for a fantastic score in the summer. It's like 60% for an A. Remember that. The student used a wash bottle containing deionized water when approaching the endpoint to rinse inside the conical flask. Explain why this improved the accuracy of the titration. Alright, if you've got a burette and you've got a conical flask and you've got your liquid in there, the drips come out, but they splash up onto the sides of the flask, and you can get drips of reactants stuck to the side of the flask. In other words, they've come out the burette, you think that they've mixed, but they're stuck to the side of the flask. They haven't mixed. So you can wash down the insides of the flask with a wash bottle, and it washes the reactant into the mixture so it can all react, so that all of the reactants can react. Alright. Cool. Give the meaning of the term concordance. Concordant means results or titers that are within, 0.1 centimetre cubed of each other. 31-minute video. It's getting a bit long. 2-methyl-propan 1-ol can be prepared by reacting 1-bromo-2-methyl-propane with dilute aqueous sodium hydroxide. Dilute aqueous. Right, sodium hydroxide is OH minus. The sodium's a trick. Don't fall for it. Name and outline the mechanism. Right. You're getting a bromo and you're turning it into an ol with sodium hydroxide. You are looking at nuke sub. You can't write nuke sub, you have to write nucleophilic substitution, and you have to know how to spell it. Alright, so my advice here, draw your product down at the bottom. 2-methyl-propan 1-ol. 2-methyl-propan 1-ol. Make sure on your ol you've got the carbon bonding to the oxygen and not to the H, or not somewhere in between. 2-methyl-propan 1-ol, and it's being made. Now I'm going to write the starter material, which is 1-bromo 2-methylpropane. 1-bromo 2-methylpropane. I'm just checking that it doesn't say skeletal or anything. Alright, full structural, because I'm not showing all the bonds here. So this should be fine. Reacting with sodium hydroxide, OH minus, lone pair. I always asked you to go delta positive and delta negative. There's barely any marks for that, but it gets you thinking, doesn't it? That goes there. That goes there. Done. Oh no, not quite done. Plus Br minus. Let's see if that's what it wants. Cool.